the difference is on the objective function. In linear programming, you have linear function. In quadratic programming, you have quadratic function and linear function. So it could be the linear function could be also in objective. Before we go into the quadratic programming, I would like to ask you some question. Could you tell me what is the difference between simplex method and interior point method? Could you maybe one of you could explain to me what is the main difference? What is the concept or ideas? Yeah, Soren.
Okay. The simplex method is that you find all the intersection with the different constraints, and then you go along the border of the space, and then you always take the most gradient descent in the borderline until you find the minimum.
Yes.
And the interior algorithm goes inside the constraint instead of on the border and tries to minimize down to the minimum by using Newton methods.
Yes, exactly. And then when we talk about Newton method, then we need to think about the direction and also the step length. And then we already learned about this in the previous lecture. And then also the linear programming, is it convex or not? Anyone? Yeah. Linear programming, is it complex, convex problem or not?
I would say it's convex.
It's convex problem.
Yeah.
And why is that?
Because if you take 2 points from the set, then you can draw a line without going out of the set.
Yeah, that's true. And then if I ask you what is the general formulation if a problem, we can say a problem is convex, what is the requirement for the objective and what is the requirement for the constraint? Do you still remember? In convex programming, the objective function should be what? The objective should be what?
Should I just go again?
Yes, that's fine.
The equality constraint should be linear and the inequality constraint should be convex or concave.
Yeah. How about the objective?
It should be linear. No, it should be convex.
Yeah, it should be convex. So the objective should be convex, and a linear function is convex. And how about quadratic function? Do you think quadratic function is convex or concave?
I would say they're convex because if you have a parabola, then it's convex if it's positive.
But is there any requirement for this convexness of quadratics? Let's say that you have like x1 square plus x2 square, but this is in 2 dimension. Is this function convex or not?
It's circular.
Yeah, circle. So it's
Convex.
convex or not? It's convex, right?
Yeah, convex.
So, but how about minus x1 square minus x2 square?
It's
Is it
concave.
convex or concave?
It's concave because
Concave.
it doesn't.
Yeah, it's concave. That's true. So, being parabolic is not necessarily convex. It's depend on the shape. Is it going up or going down? Because I mean, it's depend on your definition of minimization problem. If you want to minimize fx, and fx is a parabolic that is go up, So you have minimum point, then your objective is convex. Okay. And then if you can imagine, I'm really sorry, I cannot write in the blackboard, but now let's imagine that you have x1 square plus x2 square. Okay, you can write in your paper, for example.
Can we
x1
just do it in Paint?
Paint. This one,
Yes.
it should work. Okay, let's try it. I never do this. Okay. Let's. Okay, I hope this will work. So let's say that we have I have a function x1 square plus x2 square. Okay. So now I can write this simple function into a matrix and vector multiplication, and that is I can write it like this: 1 half. Okay, this is half of, let's say, x. Okay, x transpose times, I have matrix H, let's say here, this matrix. So X is vector, a vector of x1 and x2. H is a matrix. So I can write this simple equation, x1 square plus x2 square into matrix and vector multiplication, which is half, or half times x transpose times H times x. Okay. And once again, this x is a vector that consists of x1 and x2. So from here, what is the matrix H looks like? So this H is matrix. Do you have any guess what this H looks like?
It should be 2 by 2.
Yeah, it should be 2 by 2. And then what are the entry?
That should be 1 1 0 1 0 1. Sorry. So 1 on diagonal.
One in diagonal. So identity matrix basically.
Yes.
Yeah. But then we have half here. So what would happen?
We multiply by 2 and say 2 on the diagonal.
Yes, exactly. So the diagonal become 2. This is 0. 0. And this is 2. Okay. So we have like this. So H obviously is positive definite because the eigenvalue, I mean, the non-diagonal are zeros, meaning we have this diagonal matrix, and this diagonal entry are the eigenvalues, and the eigenvalues are positive. So H is positive definite matrix. So if you look into this kind of problem, these quadratics, then you can say that if H is positive definite, then your problem is convex. Okay, your objective function is convex. So it's you can see convexity or not, it's convex or not, by looking into the eigenvalue of this matrix H. So I hope that's clear. Because then if you write this minus and minus, then your H matrix will have negative eigenvalues, which are -2 and -2. Then your problem is non-convex. Okay. So that is just a short introduction. So before I go into the quadratic programming problem, I just want to do some exercise from last week. Last week we have we solved this linear programming example using graph, and then I would like to introduce you with the MATLAB function linfrog. So linfrog is MATLAB function, consists of two main algorithms. The first one is simplex method, and the second one is interior point method. So, okay, last week we already have this kind of solution, and then if you want to do it in MATLAB, it's quite straightforward. Basically, can you see my screen clearly? Yeah, good. So, LeanFrog is like this. You want to minimize objective function subject to inequality constraint, equality constraint, and this is like state constraint, x between lower bound and upper bound. And then if you look into our problem here, we want to maximize this objective function. So this objective function is 50x plus 40y. So if you look into this guy, so f is a vector. So this is vector. You transpose this vector, so it's become a row vector times a column vector. So this is a scalar, as you know. So if we have this one, what is f? F is basically a vector of 50 and 40, right? So that is quite straightforward. So f is a vector of 50 and 40. And then you can build also a matrix A, and matrix A is from here. This you have inequality constraint. So matrix A should be one matrix of 1, 1.5, 2, and 1. And then you can also define lower bound and upper bound by I can show you how you do it. So okay, there is one note here that this is the general form when you want to use LeanFrog, and in this general form you want to minimize some function, but then in our problem you want to maximize. Therefore, you need to multiply the objective function with -1. Okay. So your f is minus 50 and 40. I hope this is clear.
Yes.
And matrix A is quite straightforward, as I said to you. There are two ways how to write this matrix A. The first one, if we look into the problem here, we can say that matrix A is a matrix with the size 4 times 2. 4 times 2. So the first row will be 1 and 1.5. The second row is 2 and 1. The third row would be -1 and 0, because you need to multiply this with -1. And the fourth row will be 0 and -1. You write like this. So this is the matrix A. Okay, this is the matrix of 4 times 2. And then B is actually this guy. So B, right hand side of the constraint, which is in this case 750, 1000, 0, and 0. So you got this number. And then basically you can just write x equal to LeanFrog. Here you can choose your algorithm. In this case, I think the default is in simplex. But if you want to have interrupt point, you need to define this. And if you just run it, you can see also how many iterations in order to converge to the actual point, to the optimal point. So this is quite straightforward, and I already put this in the Blackboard, so you can just download it. Now this is the first one. The solution is 375 and 250, which is this guy. So it's converged to the actual solution. But we can also define matrix A a bit different. So I can say that matrix A is only the first two constraint. So the size of matrix A would be 1 and 1.5. The second row is 2 and 1. And then I just want to delete the third and the fourth row. The same with B. So in this case, I have a bit different formulation. Okay, but then I also want to define X and Y as a lower bound, because here X should be positive, meaning that the lower bound should be equal to 0. The same with Y. Y should be positive, then the lower bound for Y is also 0. And then you find this lower bound in this setting. You see here the setting is that first your objective, the second one is inequality constraint, the third one, the fourth and fifth, that is the equality, and then the rest is lower and upper bound. So you can also do it like that, meaning that I write this lower bound, and the lower bound is 0 and 0. And then I can define this in here. Just run it. And then it's the same. So what we learn from here is that you can write the optimization problem in different way. Okay, so that is the point. It's not unique. You can define the equality or the state constraint as you like. Okay. And then how about this one? Do you still have the solution for this from Adam last week? But let's try to discuss this once more. Two process stages are involved in the production of gold of different carats. Let's suppose the gold production factory in Denmark profit $40 for 18 carats per gram and $30 from 14 carat and $20 from for 10 carats. So first of all, you can define the variable. Let's say that X is the amount of gold with 18 carats, and then Y for 14 carats and Z for 10 carats. So the objective function, or the profit, would be, you want to maximize 40 times X plus 30 times Y plus 20 times Z. That is your objective. And then I also write here. But then the same with the previous example, since you want to maximize, but formulation in linear programming is minimize, so you need to put minus in front of this objective. And then this is per gram. This is per gram, meaning that if we can convert to kilograms by multiplying with 1,000. Therefore, this is 4,000, 3,000, and 2,000. So this is the price for each kilo of gold from different carats. And then for the inequality constraint, because we have limits here for equality constraint. I think Adam told you why this is equality. It's because here, this one, the available time should be fully utilized. So meaning that the total should be 7,200 and 6,000. Okay. And then this numbers is coming from this combination. So basically, for 18 carats, you have 3 hours. So 3 times x plus 2 times y plus 1 times z. And then for the second row, you have 2 times x times 2 times y times 3 times z. Okay. And then we can also define the lower bound, because all of these variables should be positive. So you define lower variable, and then you can just run this program, and then you get the solution. In this case, we have interval point. So it's quite straightforward. So the objective of this lecture, of our lecture today, is just to introduce you with some function in MATLAB, how to solve linear and quadratic programming. But next week we will learn more advanced software, not only MATLAB, and Adam will help you with setting up the solver. Adam, are you here?
Yes, hi, Agus.
Hi, Adam. So next week you are going to present them with some commercial software, right? Not commercial, but open software.
So we will try IPOPT as an optimizer, and then SNOPT, what are the most famous optimizer used. So
yeah,
the idea.
That's good. So I mean, I want to expose you with different kind of solver for optimization. So not only MATLAB. So Adam will help you to introduce you basically with the IPOP and SYNOP. That is quite famous optimization software. Adam, I just wonder, do they need to set up something?
So it should be all pretty much straightforward. They just need to compile IPOPT, and then SNOPT comes directly with the optimization tool, so it should be fine.
Yeah, but did they need to install something?
I will send an email saying exactly what they need to install for the lecture. So
okay, that would be great. Yeah.
So we are all ready.
Yeah.
In the end, next week.
Okay, fantastic. Okay, so that's great. So Adam will introduce you with another solver, not only MATLAB. Yeah. Let's continue to the quadratic programming. So in the first lecture, I showed you this diagram. So basically, this is a basic concept of model predictive control. And then in this case is that sometimes we have tracking problem. And tracking problem is that you want to track, or you want to I mean, you are given a trajectory or set point, and then you want to go from your initial position or initial state, go to this reference or reference trajectory. And then you can define your objective function into a quadratic objective function, just like this. So this is quadratic. There is I'm not sure if you are familiar with this kind of signs. This is norm actually. So if you have a vector and then you give norm, basically is equal to when you multiply a vector times matrix times vector. So it is like what we wrote like this. Okay. So I hope you don't confuse with this kind of sign. So this sign is basically norm. In this case, so y, this y and r could be a vector, So in this case, it's like x, and then this w is the weighting function, which is equal to the matrix H. So this matrix H, just like this is the weight of the objective function. I hope you are not confused with this kind of symbol. And then subject to constraint, the constraint could be linear and could be also nonlinear. Usually, if we think about dynamical system, it's a equality, so like this. So meaning that your problem is a quadratic problem with equality constraint. I will give you some example here. I think for some of you who work with me, I think 2 years ago when we have a project for robotic control system, I showed you this page, if you remember. Yeah. It's been a while, but basically this is how you model different kind of mechanical system. It could be cruise control system, motor speed, suspension, inverted pendulum, and aircraft pitch. But as you can see here, I hope you still remember this one. This is quite simple how to model the cruise control system. You consider a car moving forward, and then it has a force U, but then there is a drag force B times V. V is the velocity, and then when this car is moving, it's should be respect the Newton laws, and that is the mass times the acceleration equal to the summation of all the forces. So you will get this kind of state space, or in a compact form, a standard form, you will have like this. So this is basically say that your position, or so this velocity, the first derivative of position with respect to times equal to some constant times your velocity plus this some constant time your controller. So this is linear. This linear system, and then if you discretize the system using, let's say, Euler discretization, I hope you are familiar. So if you discretize the system, then you can have a algebraic equation. So this is differential equation because you have this notation. But if you once you discretize, you will end up with algebraic equation, and this algebraic equation is actually in general looks like this. So you can write it like this. Okay. Imran, do you have any question?
No, I'm all right.
Okay, that's good. So you have this kind of system. So meanings, and then in our problem, for example, here, and that is you want to find a controller such that you will able to control your velocity. So the controller could be the pedal of your car, and the output is the velocity. So this is a cruise control problem. So if you drive and then you see like your car should be 80 kilometers an hour, then you can set up the cruise control system. So you set the reference point here is 80 kilometers an hour, and then the algorithm will try to calculate how much input that you need such that your car will go 80 kilometers an hour. So this is a practical problem, and then you can see a lot of this kind of problems in mechanical engineering. So that is one problem in cruise control system. And of course, if you think about thermostat, when you want to control the temperature of a room, then you can also think about this kind of formulation. So you want to minimize the difference between your current state and your desired temperatures subject to some constraint, and the constraint is basically the model of the model of the temperatures in the room. Okay. So in the sense that quadratic programming problem has a lot of application, therefore it has a special chapter. So from linear, we don't go directly to nonlinear, but we first consider the quadratic problem. And then, as I said before, that in quadratic problem, if the matrix H, the problem, like this one, if you write the problem into like form like this, and then you know that H is positive definite, then your problem is convex. And when you have a convex problem, then it's easy to find the solution. And you can make sure that the solution is global solution. Okay. Now, this is the general form of quadratic programming. So you want to minimize this objective function, in this case Q. It could be also F. I mean, you can write this like whatever you want, basically. And it is equal to quadratic terms like this and linear terms. So the quadratic terms, as I mentioned before, this G, if this G is positive definite, then the objective function is convex. Subject to, you have equality constraint and inequality constraint. Now, if you read the books in section 16.1, the main point of chapter 16.1 is you need to, they present a proof that if we have this kind of problem, then you can sure that the solution exists. Okay, so this is the problem that is discussed in section 16.4, and how to do that is by looking into this is well-posedness problem. Well-posedness means that you want to know if a problem has a solution, and if that solution is the only solution. So existence and uniqueness. This is very important, because before you want to solve a problem, then you need to make sure that the solution exists and unique. This could be unique because we assume that G is positive definite, so this is convex. And then basically, how to do that? So first of all, we only consider the equality constraint just to simplify the derivation. If you look into this general problem, and then you apply the quadratic condition, then you will get this kind of system. So remember that when we want to do we want to find the quadratic condition, first of all, you need to define the Hamiltonian function, and the Hamiltonian function is equal to the objective function, and then minus the Lagrange multiplier times the constraint. Okay. Yeah, you have question?
Yeah. Okay. So in the book, they say that G is the Hessian, and if the system is convex, isn't the Hessian always positive definite?
Yeah, that's true. But actually, yeah, G, of course, G is Hessian, because if you derive this Q twice, then you will have that the second order derivative of Q will be equal to G, which is the Hessian.
Yeah.
Right. So if G, which is the Hessian, is positive definite, then the problem is convex.
Yeah. But
So-
is
Mhm.
but if are we not looking at convex problem? But no, we're only looking at quadratic. Never mind. Okay. Yeah.
Yeah. Yeah. So there is a condition. I mean, we can say this quadratic problem here, quadratic function, a convex if G or the Hessian is positive definite. So yeah. So okay,
Continue.
back to the Hessian. So you have the Hessian, and then you calculate the gradient of the Hessian, and then you will get the first equation here, which is G times X minus A transpose times lambda equal to minus C. That is the condition from the first catalytic condition. And then the second catalytic condition is basically the constraint itself. So A times X equal to B. Okay. So this is from the catalytic condition. And then there is a trick that we can use in order to show that this problem has a solution and the solution is unique. And then how to do that is this is the trick. I will not go into the detail, but if you define this kind of new variables, then you can transform your catalytic condition, this guy, into this guy. Okay. And then what is different between this and the next one is that here this matrix is not is irregular, it's not symmetric, but once you do this variable substitution, then you can get new system of matrix, but then this matrix is actually a symmetric matrix because yeah, you can see here. And then here is the result. So the result says that if A have a full row rank and assume that the reduced Hessian matrix is positive definite, then the category is non-singular. If this category matrix, this is called category matrix. This category matrix, if this is non-singular, then you can find this variable. Basically, you multiply the left-hand side with the inverse of this, and then the inverse will goes to the right-hand side. So once you get this variable, then you will get the x also, and also sorry, the x star, which is the solution. Okay. So this is only the condition to state that actually this is written in theorem. This theorem is in from the book. But the main thing in here is that if the G or the G matrix is positive definite, which is convex, then you can always make sure that this problem has solution, and the solution is convex. Sorry, and the solution is unique. Now, how if you have negative G, or let's say that G is indefinite, meaning that the eigenvalue could be positive and could be negative. Then your problem is not convex, then you will have a problem. There is some class of algorithm that you can use when you have non-convex quadratic programming, but we won't discuss in this lecture. So we always assume that G only for this lecture and also for the next time, G is positive definite, meaning that we work with convex optimization problem. Okay. Do you have any question? I hope it's clear.
It is.
Yeah. So let's do some example. So in this example, we have we need to minimize some objective function. This is very long. You can see here. This long objective function subject to this constraint. Now what we want to do now is we want to change, or we want to find this kind of matrix. We want to find this G matrix, and we also want to find C factor and A and B. So yeah, this is the solution. But do you know how to find G matrix if you are given this kind of equation? So there is a trick actually, and the trick is like this. So you have nonlinear term from here into here, right? And then you have linear term. So obviously from here, the linear part would be the coefficient of this linear term, which is minus 8 for x1, minus 3 for x2, and minus 3 for x2. So you have minus 8, minus 3, and minus 3. So that's clear. How about G? How can you construct G matrix from here? So before I go into this one, 4 days or 5 days ago, I shared with you some videos, I think from Khan Academy, that is the first one, on how you change or how you find a matrix factor multiplication from scalar function like this, right? Did you see the video?
Yes.
Is it complicated, or you think you find it easy?
No, it was a good video. Easy,
Yes.
easy one.
It's easy one. So the trick is that how to build this or generate this G from here is that, first of all, G is symmetric matrix, meaning that the transpose of this matrix will be equal. So this guy will be equal, that guy equal, and this guy will be equal. And then from here, if you have square like this, x1 square, x2 square, and x3 square, that would be the diagonal. The diagonal should be multiplied by 2. And why is that? It's because in the general form, we have half in the front. Okay, this is half in the front, so the coefficient of this should be multiplied by 2. So 3 becomes 6, 2 find 5 become 5, and this is 2 become 4. How about the remaining? So for example, this one, this is x1 and x2, and then you look into the index. This is index 1, 1,2. That is 1,2. This is the guy. Okay, this is the position, and this is the coefficient. The same with this one, x1, x2, x1 times x3, and the coefficient is 1. So this is 1,3. This one is the coefficient. The same with this one, and this is the guy, and then you can copy into the remaining triangle. Then you can see this. You can generate this matrix G. So that's it. So this is quite straightforward. Okay. And then my question is that why you don't multiply with 2? So if you have a diagonal, you multiply by 2. But why for non-diagonal you didn't multiply by 2? Do you know the reason?
Because it's done automatically because you have x on both sides of the matrix.
Could you repeat?
You have x on both sides of the matrix, so
Yeah.
the other terms are automatically multiplied by
2.
Yeah.
Yeah, because but and that's right. And if you look into the structure, because you copy actually, so this is 2 and this is 2, so you copy. So basically you like multiply by 2 also. Okay. And then from the matrix A is quite straightforward also. This one is 1, 0, 2. 1, 0, 1, and this guy is 0, 1, 1. So you have this one, and you have B. And then from here, basically you can write the program using quadproc, and then how to do that is quite straightforward also. I write it right in here. So you define H, you define F, and then you define equality matrix like this, A equality, because we have equality constraint here. Then you can just call this function quadproc, and you will find the solution. Okay. Now, how about this one? This is only for this is an exercise for you. So I will give you 3 minutes, and then you look into this problem. I want you to define what is H, what is the F, linear terms, and what is A. Okay. 3 minutes.
Address. Hello.
Yes,
Address?
hello?
Yeah. I looked into the videos, and shouldn't the constraint be less than equal to, or we can do with this one as well, being greater than equal to?
Yeah, the constraint, if you look into the general form here,
It should be less than.
should be less than. Yeah.
Okay.
That I mean, when you define optimization, then you need to look into what they mean with the equality constraint. Is it less than or greater than? Because in the book, the format is greater than, right? But here it's less than, so you need just to take care of
We
it.
need to adjust that. Yeah.
Yeah.
Okay. But and it's two-dimensional.
It's this one is 2-dimension. That's true.
Okay. I guess, do we have to set an upper bound and a lower bound for this one?
Yeah. It's up to you.
Okay.
So either you can include it or separate it with matrix A.
Yeah, done.
Okay, so you're done.
Yes.
So what is your H matrix?
The H matrix is 2, 2.5. That's the first row. Then it's 2.5 and 20.
Sorry, 2.5.
2, 2.5, 2.5, 20.
Yes, that's true. Sorry. And then how about the C matrix?
It's 2 and 3.
Yeah, it's from here. And then how about A?
A is 1, minus 1, minus 1, minus 2.
Yes, that's true.
Because I've shifted it to the inequality to less than equal to 100.
Yeah, that's true.
B is 1 and minus 100.
Hmm?
And lower bound I've given 0 and 0.
Okay, that's true. So how about everybody? I think it's in the same page. So that's how you do it. So how you change your constraint. Sorry, how you change the objective form from algebraic equation like this to matrix multiplication. Okay, that's good. And then have you tried to use MATLAB to find the solution?
Not, I've just done this one up till now.
Okay. So I will give you two minutes. So just for your exercise.
Okay. I just need to find out this quadprog. Have you uploaded that quadprog file?
No, but you can find it you can
MATLAB.
Google it. Yeah.
Yeah.
Or I can share it with you also here. Yeah, that one.
Thanks.
Yeah, have you find it?
Still doing. GB. Just a minute.
August, what is the active set that they're talking about in the book?
Active set? Oh yeah.
Yeah.
Active set is an algorithm that you can use to find the optimal solution. So in linear programming, you have simplex and interpoint. In quadratic programming, you have active set method and interpoint. But we will not discuss active set method because interpoint has superiority with compared to active set. And then MATLAB is actually they not use active set anymore from I think from 3 years or 4 years ago. So it has been deleted from MATLAB because of low efficiency.
Okay, so they're old algorithm.
They are all algorithm, yeah.
Okay.
So this is what I get. It's actually
Yeah,
16.
I've got the result. I've got 34 and 33.
Oh yeah, that's true.
Right.
This
Okay.
one. Wait.
You have
wait,
a 20 in the beginning of age, which should be 2.
Yeah.
Yeah, this one.
Yeah.
Yes, that's right. Yeah, that's true. Okay.
August, is it 34 and 33 as the optimal point?
Yeah, 34 and 33.
Nice. Oh,
That's true.
thank you.
Okay, that's good. So yeah, let's discuss the algorithm. I actually just mentioned to you before that you have two main algorithms. The first one is active set, but active set is not used anymore by many people. So now the standard goal for solving quadratic problem is by using interpoint method. And then from last week, we have discussed the idea behind interpoint method, and that is actually by solving the k-TT condition directly. And then when you solving this k-TT condition, you use Newton method. Okay. So first, if we have this kind of optimization problem, you want to minimize the objective function subject to inequality constraint, and then you can calculate the k-TT condition, and that is given by here. The first k-TT condition is when you take the first derivative of the Hessian function equal to 0. The second k-TT condition is the inequality constraint itself, and then the third one is the complementary condition, which say that either the constraint is active or the Lagrangian multiplier is equal to 0. And since this is inequality constraint, then we have positivity in the Lagrange multiplier. So this is the k-TT condition. And then just like last week, we introduced what we call a slack variable to make because we want to solve this using Newton method, meaning that we somehow we need to change this signs from inequality to equality, and in this case you introduce this slack variable, so the inequality become equality, and then you write it into a system of nonlinear equation, and then you can run your algorithm, your Newton method, basically. Okay, so that is the idea. So it's the same with the interpoint method for linear programming. So that's it actually for the basic theory about quadratic optimization problem or quadratic programming. You have a general form which is like this, and then what we learned today is that if you want to make sure that this problem has solution and unique, then G, or the Hessian matrix, should be positive definite. And then the second one also, we learned that if you want to solve using numerical scheme, there are two ways, but interpol method is the best one for this kind of problem. So, do you have any other question? Do you have any question? Otherwise, we still have 10 minutes, and I would like you to go to some exercise. So I already posted this in Blackboard, so you can just download it. Exercise 5, like this. So there are 4 questions. The first 3, question number 1, 2, and 3, are quite straightforward. So you are given an objective function. You want to minimize this objective function with different kind of constraint. The first one is equality constraint. The second one is a mix between equality and inequality, and then the third one is only inequality constraint. And then this is equation number 4 is more too practical. So you need to model the quadratic programming and then solve this using MATLAB. So you can start from now. Try to go into each example, and then I will be here until 10 minutes. So if you have any question, then we can discuss this.
Are these the same exercise that we get from Adam?
You get from what?
From Adam?
Yeah. Did Adam just send you this?
No, but is it the same exercise that he's giving us?
Yeah, it's the same. Yeah.
Okay.
So,
I didn't send it, so.
yeah, he didn't send it, but I already posted in Blackboard, so they can just download it.
Good.
From 1:30, I will off, and then Adam will help you with if you have questions. So basically, this is your main task that you do it yourself, and then if you have question, you can ask Adam. But this is quite straightforward actually. Maybe before I finish with this one, I would like to just show you how to do this, and then basically you just look into this problem, this page, and then once you able to define the matrix and vector, then you just can plug this into the function, and then you can good to go. Okay. Yeah. Yeah, I will be here in. So if you have question, but you can just start working with MATLAB.